is required again. So just to recap, we found that the work done by the forces, in our case it's just surface forces, is the integral of trace s dot delta f dv. And now we're going to write the principle of work. Principle of work tells you that the work done is equal to the change in kinetic energy, where it's 0 here, because there's no motion, everything is static, plus the change in potential energy. And so here we're going to call potential energy, we're going to call it the stored elastic energy. The stored you can keep calling it potential energy if you want. And a good idea of what the stored energy is to think, you probably have done that in your life. If you take half a spherical cap, say half a tennis ball, and you deform it inside out, it's going to stay where, provided the cap is high enough, it's going to stay in its inverted state, right? And then if you put it on the table and you wait, it's probably going to spring up at some stage, right? So there was some energy stored in there. Even though I start with my cap in original cap, I go to the inverted cap, and I have, in both cases, I have an equilibrium. They're both static equilibriums. The one has stored energy, or a higher level of stored energy than the other. Anyway, we're going to call it the stored energy, the stored elastic energy, or the stored energy. And we're going to measure it by W, which is going to be the stored energy density per unit volume in the reference configuration. Right? It's easier to think of energy stored in the volume than just the surface. So that's why I was doing all this transformation to turn integral into a volume integral, right? Total energy, total stored energy is W dV. Right, so if I write the principle of work now, I'm going to say that the change in the stored energy is going to be equal to the work done by the surface forces. Which is trace S delta F dV. And this is true for any region in the body or subregions. And so you can conclude that it's going to be true locally. Yeah. So that everywhere you will have delta W equals trace S delta F. That's terrible here. And then you need to invoke the fact the worked on is path independent. So this has to be true for any small deformation I'm going to make. And so path independence, no matter which way I go from one to the other, I should still have this equality. And that means that really this has to be true for a tiny amount of deformation, a tiny displacement, and so it has to be true for the full differential. dw is trace of S df. Okay, so that's really important. We're now getting closer to describing an actual solid. An actual solid is going to be determined by the form of its strain energy density, stored energy density. So then there are several theories to describe materials. We're going to put ourselves in the framework of what's called hyperelasticity. It's also called green elasticity. And that's the assumption that W is a function of F only. So that's a strong assumption, but it describes a lot of materials in the real world. Now you could also imagine that W is a function of a gradient of F, or of position, or velocity, and all sorts of theories like this. They are much more complicated, and I won't be studying them in this course. So if you make that assumption that W is a function of F only, when you compute the full differential, it's a function of the components Fij, then you're going to have to sum the partial derivatives for all those variables. That's what the full derivative of W is going to be. And that's for the left-hand side of my framed equation above. The right-hand side, trace of AB that's sum of A, J, I, B, I, J. Right? Trace of A would be sum of AII, but now it's AB, so it's product of two vectors. And so it's going to be AJI, IJK, but then you have to sum blah, blah, blah. Right? So it's going to be, if I apply this formula here, it's going to be equal of S J I D F I J. And I want this to be true for all small displacements. And the only way that's possible is if jeez, I think again. SJI is DW Fij. Or you can write it in a symbolic way as Fs being the derivative of W, which is a scalar, with respect to a tensor F, provided, I should write it the other way around as well. with convention. It's a bit confusing, but yeah, you have to swap the indices there if you want everything to be consistent. So if you adopt this convention, then you can write that S is the derivative of W with respect to F. And then sigma, the Cauchy stress, is going to be J minus 1 F dW dF. And that's also hard to memorize, but if you look at the indices, they're going to be like this. F, oh, I need to put the sum. But I have a product of two tensors here. dW dF kj, which is going to come out in this order. Wow. That was hard. But that's it really, we're nearly there now. All we need to say is that a given material is characterized by its stored energy function W of F, right? If you bring me a piece of rubber, I'm going to tell you, oh, well, it's that W. Or if you bring me a gel, I'm going to say, oh, no, it's that W, right? Each of them will have a different W. And once you have W, you're okay, because then you can compute S and check that the equation of equilibrium are satisfied. So for a given W, you compute S is going to be a function of F, the deformation. So then either you impose the force and then you deduce the deformation, or you impose the deformation and then you check that the force generated satisfy the equation of equilibrium. But altogether, you're sorted, or you could write sigma write the same equations for sigma. Either way, you're going to be able to solve problems from now on. Now, the whole question is, what is W? Can W be any function of F? As you will see in the coming 2 weeks with Giuseppe, there are some restrictions that you have to impose due to physics, basically, to constraint of objectivity, material symmetry, and so on and so forth. Giuseppe will go through this, but within those constraints, pretty much free to choose W according to the behavior of a given material. And then you don't know what W is if I come up with a new material or a different composition for my piece of rubber. But then you just go in the lab, you do a controlled experiment, and you make some guesses as to which W is going to produce this response. Or maybe you do curve fitting exercise, you do all sorts of things like that to adjust the parameters in the W so that you know that this is the strain energy function, the stored energy function of your given piece of material. And then that's it, you're done. You just need to plug that into a computer maybe, or just solve it by hand, but you can solve all sorts of problems for that material. So that's the end of the lecture. I apologize now for all the mess. There is the technical mess, and then that threw me off, and I made lots of mistakes when I wrote those notes. I'll tidy them up now and post a cleaner version of the notes.